Alright, this is going to be Unit 2, Chemical Structures of Matter, Topic 1. So, unit learning goal. I can compose and write formulas for ionic compounds. This is the one we're going to focus on today. The other unit goals for this unit are going to be compose and write formulas for covalent properties, distinguish between empirical and molecular formulas, determine molar mass and formula mass, determine the percent composition of a compound, and apply stoichiometric properties. So chemical bonds and electrons, Unit 2, Topic 1. Chemical bonds and electrons, most matter exists as compounds, not as pure elements. So that just means in nature we don't find these atoms just hanging out by themselves. That's because most elements are chemically unstable, so they're not. To become stable, elements will form compounds or chemical bonds with other elements to make compounds. So compounds are atoms of elements form chemical bonds joining the atoms to make a stable partnership. Chemical bonds form when atoms transfer or share electrons. Atoms want to share or transfer electrons because atoms are the most stable when they have a full shell of valence electrons. Energy is released when chemical bonds are formed. So when atoms come together and create a new substance, energy is released. Energy is released because the atoms that bond together have less total energy than they did on their own. So basically, atoms are seeking out a lower energy level. Covalent bonds are formed when atoms share electrons to achieve stability. What does that look like? Well, let's take a look at this hydrogen. These two hydrogen atoms, they both have one valence electron because they're in group 1. Everybody in the first row of the periodic table wants to have 2 valence electrons. Then we take a look at this oxygen. This oxygen atom has 6 valence electrons. Of course, everybody wants to have a full shell, and other than the first energy shell, you could put up to 8 electrons. So it has 6, it needs 2 more. So what's going to happen is when these guys get close enough to one another, they're going to start sharing electrons. See, these 2 electrons here are going to be shared between the oxygen and this hydrogen. Sometimes the hydrogen's going to have the sensation that it has both of its valence electron shells full. Sometimes the hydrogen is going to have the opportunity to have both electrons. Sometimes the oxygen will have the opportunity to have those electrons. This other hydrogen is going to do the same thing. Oxygen, when it combines to share electrons with 2 hydrogens, will get the sensation that it has a full shell because it's sharing 1 electron from each one. And vice versa, 2 of the electrons are being shared with the other atoms, the hydrogen atoms. So the hydrogen feels like it has a full shell. When covalently bonded atoms combine, we call those molecules. Ionic bonds are a little bit different. Ionic bonds occur when electrons are transferred from one atom to another. So if you get a really strong electronegative atom like chlorine, and it comes in close proximity to a really weak electronegative atom like sodium, you're going to get a stealing or taking of the electron from the weaker element to the stronger element. When that happens, we get a proton to electron imbalance. They form ions. So chlorine gained an electron and it now has a -1 charge. Sodium lost an electron and dropped down to a full shell, and it now has a +1 charge because it lost that 1 electron and now has 1 more proton than the total number of electrons. Well, what happens to oppositely charged particles? They're going to attract to one another. When that happens, an ionic bond is formed. Ionic compounds do not form molecules. Molecules are strictly in relationship to covalently bonded compounds. Let's talk about chemical formulas. Chemical formula describes the ratio of atoms that make up the compounds. So we're taking a look at this water molecule. How would we write that out? Well, the chemical formula for water is H2O. Well, what does that mean? Well, that just means when reading a chemical formula, chemical symbols indicate the identity of all the atoms that are part of the compound. So in this case, we have hydrogens and oxygens. The subscripts indicate how many of each type of element are present. So in this case, because there are 2 hydrogen atoms, we have a subscript 2 to represent the fact that there are 2 of them. Well, what happens when there's no subscript? Well, in the event that there's no subscript, that just means there's only 1. So let's take a look at this molecule of butane. What type of atoms and how many are present? So first thing we're going to see is there are carbon atoms, and there are 4 of them. And we have hydrogen atoms, and there are 10 of those, for a total number of atoms of 14. Well, what about copper nitrate? Copper nitrate's a little bit different. It has the one copper atom, It has 2 nitrogen atoms, and the reason it has 2 is because anytime you have atoms inside of parentheses, we multiply it by the number on the outside of that parentheses. So in this case, there's 1 nitrogen atom, but because of the subscript 2 on the outside of the parentheses, it's 2 times 1 for a total of 2 nitrogen atoms. Oxygen has 6, and then for the same reason, there are 3 inside the parentheses, multiply that times 2, and you get 6, for a total of 9 atoms. So write the chemical formula for the molecule of methane on the right. So taking a look at that molecule, what's in the molecule? Well, we know that there's carbon and we know that there's hydrogen. Well, how many carbon? There's only 1, and because we don't need a subscript to represent 1, we just put the letter. But there are 4 of the hydrogen. So we have to put the subscript 4 to indicate there are 4 of them, and that gives us a molecular compound formula of CH4. All right, let's get right into our learning goal. So you need to be able to compose and write formulas for ionic compounds. Ionic compounds transfer electrons from one atom to another. Atoms that participate in ionic bonding will do so in a predictable way due to the number of valence electrons it needs to give away or accept to reach the octet, to reach that stability level it wants. All elements except for the noble gases form compounds. However, some elements are more reactive than others. Reactive simply means that the elements readily form chemical bonds. So the closer it is to getting to an octet, the more reactive it's going to be. So all stable compounds are electrically neutral. This means that they have no net charge. Because the overall charge of the ion must be 0, the total cation and anion charges must cancel each other out completely. So oxidation numbers indicate the electrical charge of an atom when the electrons are lost or gained or shared during chemical bond formation. The table on the right indicates the most common oxidation numbers of the most common elements on the periodic table. We're going to avoid our transition metals because they have some different rules. We can use the oxidation numbers to write a stable ionic compound. To write a stable ionic compound so let's go ahead and do a practice. Let's write a stable ionic compound that contains both magnesium and chlorine. Magnesium is right here in the periodic table, so let's go ahead and bring that guy down. Chlorine is right here in the periodic table. We're going to bring that guy down. So we're going to take these guys and we're going to combine them to form some combination of these 2 elements. Remember, the overall charge of the compound has to be 0. It has to be neutral. How do we achieve that? Well, we're going to use the oxidation numbers and we're going to identify what they are. Magnesium has an oxidation number of +2. Chlorine has an oxidation number of -1. If the oxidation numbers are not the same, you must determine the lowest common factor that will cancel out the oxidation numbers. So in this case, +2 and -1, they don't cancel each other out to equal 0. So we have to find the lowest common factor between those 2. And the lowest common factor between a 2 and a 1 is going to be a 2. So how do we get both of those guys to 2? Well, the first one's already 2, so we would multiply that times 1. And the second one is a -1, so we would have to multiply that times 2 to get it to equal -2 to cancel everything out. Then we're just going to simply take what we multiplied each one by and we're going to drop it as a subscript in the final formula. So in this case, for every 1 magnesium, I need 2 chlorines to create a stable compound. Let's try one more time. So write the stable ionic compound that contains beryllium and phosphorus. So beryllium is right here on the periodic table. Phosphorus is right here on the periodic table. We know they're going to come together and form some combination of those guys. Let's take a look at the oxidation numbers. The oxidation number for beryllium, because it's in group 2, is +2. The oxidation number for phosphorus is going to be -3. It's going to be in group 15. What is the lowest? They don't cancel each other out to make 0, so what's the lowest common factor between a 2 and a 3? The lowest common factor is going to be 6. Well, what do we multiply each by to get it to equal 6? So we're going to take 3 times 2 to equal 6. So we need 3 berylliums. And we're going to take 2 times -3 to equal 6. So we need 2 phosphorus. So for every 3 berylliums, I need 2 phosphoruses to cancel out all the charges that make a stable compound. All right, ionic compounds can also form between metals and groups of nonmetals that have a charge. So this is 2 or more atoms that come together, but it's not zeroed out. There's going to be some kind of an ion charge to it. So these groups are called polyatomic ions. The process, however, works the same, whether it's a polyatomic ion or it's just 2 binary ions. So write the chemical formula for a compound containing lithium sulfate. So here we go. Lithium plus sulfate equals some combination of those guys. So step one, always, we're going to figure out the oxidation numbers. The oxidation number for lithium, because it's in group 1, is +1. But there is no oxidation number for SO4 because that's not on the periodic table as a group. So what we can do is look at the charge. And looking at the charge, we replace that as the oxidation number. So now, do those guys equal 0? And they don't, so the lowest common factor is 2. 2 times 1 plus 1 times 2 is going to equal 0. So we're going to write those guys in and put the subscripts down there. As you can see, there is no subscript following the SO4 because we only need one of those groups. But we do not give up the subscript associated with the oxygen that tells me there's 4 oxygens.